Let's look at working exercise 14.6 in the 4th edition of Hambley. This particular problem is from figure 14.15 in the textbook. I'll sketch that. We have our op-amp with the positive terminal up top, and that's where the input is coming into our system. We then have a collection of resistors, R1, and I'm going to label these a little differently than in the book just so that I can keep track of what I'm doing. I'll call that R2, I'll call this one R3, and this resistor let me call R4. That resistor configuration is now tied from the output of our system back to the inverting input terminal of our circuit or op-amp, which gives us our negative feedback that we're interested in order to analyze this circuit. We now know that that V sub D is going to be 0 with the summing point constraint. The only thing that I've done differently, and at the end we'll want to convert back, but right now what we'll have to remember when we get near the end is that what I've labeled R sub 3 is what the book is calling R1, and what I've labeled R sub 4 the book is calling R sub 2. This way, hopefully with me calling them R3 and R4, we can keep track of what's what when we start to do the analysis. I'm going to also start to label some of these currents that I have. Here's I1, here's I2, I3, and I4. I will label those. And with respect to the summing point constraint, let me just, if I need to refer to those, let me call that the current going into the positive or non-inverting terminal. Here is I sub minus, and we know those are actually 0 from our summing point constraint. Maybe I'm getting ahead of myself. Let's now talk about our solution. We've already determined that we have negative feedback because of this being fed back through this resistive network all the way back to our inverting terminal. That gives us our negative feedback. That allows us then to say that we can assume our summing point constraint is valid unless at the end we see that our output is beyond our supply voltages, and then we would have to conclude that we have saturation. But now we have V sub D is equal to 0, I sub plus is equal to 0, and I sub minus is equal to 0. We're now going to try to work our way from the input side to the output side, and we're going to drop down to ground as quickly as possible when we can so that we don't get too many unknown variables in all of our equations. Let's start by doing a KVL around that particular loop, which that particular loop I will label as 1. And now with KVL around 1, I have minus Vn, I'm going in the negative terminal of Vn, plus V sub D, plus R sub 1 I1, which is just Ohm's law, but that's the voltage dropped across R1 from top to bottom. That's equal to 0. From our summing point constraint, we have that being 0, and we now know that Vn is equal to R1 I1, or if we need it, we can solve for I1, which is now Vn over R1. And now we have an equation for this particular current I1. That's different than our input current into the circuit from our source. Here's our source, and this is actually our input current I sub plus into our circuit from our system, or into our system. Let's now work our way from input to output. we're going to basically sequence through a series of KVL and KCL. Now we can write KCL at that particular node. We'll label that node 2. And KCL at 2 allows us to say that the current going, let's say, leaving that particular node, node 2, we have I1 leaving, we have I minus leaving, and we have I2 leaving. So there is our KCL equation. We also know from our summing point constraint, or the fact that in all of our op-amp circuits we're going to have input currents, or currents going into the input terminals of our op-amp equaling 0. This KCL equation allows us to conclude that I1 is equal to minus I2. Let's now go back up into our circuit and start working our way again further to the right towards our output, and try now to write a KVL around that third loop. We will now go in the we will go against I sub 1, meaning that drop is going to be minus R1 I1. We will go in the positive direction of I sub 2, and that will then be plus R sub 2 I sub 2. We'll go down through R sub 3 in the positive direction of I sub 3. That will be plus I sub 3 R sub 3. We will then do KCL at 4, and finally we'll do one last KVL equation around 5, and we'll go up through or against I sub 3. It'll be minus R sub 3 I sub 3 plus R sub 4 I sub 4 plus V naught is equal to 0. That's what we want to do now, and then we'll eventually be able to solve for V naught in terms of the currents. So far we've only done KCL at node 2. Let's do now KVL around loop 3. Around that loop we have minus R1 I1, again since we were going against the direction that we assumed for the current I sub 1, plus R sub 2 I sub 2, plus R sub 3 I sub 3. We want to go down to ground as soon as possible. The currents that we do know are I1 and I2, and we know the R's, so the only unknown in that equation is I sub 3. We can solve for that, and we also know that I1 is just the negative of I sub 2, so that R sub 3 I sub 3, taking the I1 terms on the other side and replacing I2 with minus R1, we end up with R1 plus R sub 2 times I sub 1. And solving that for I sub 3, we have R1 plus R sub 2 over R sub 3, all equaling I sub 1. And from above we know what I sub 1 is. I sub 1 was just this Vn over R1. Now we know what I sub 3 is in terms of Vn. Let's now do our KCL at 4, node 4. At node 4 we have the current coming in as I sub 2. Going out or leaving that node is not only I sub 3 but also I sub 4. This now allows us to say that I sub 4 is equal to I sub 2 minus I sub 3, but remember what I sub 2 was. I sub 2 was just minus I1, and that's now I sub 4, which is just minus I1 plus I sub 3. We will now go and do KVL around the last mesh or loop, which is 5. We're going against I3, and so our drop is minus I3 I3, R3 I3 plus R sub 4 I sub 4 plus V naught is equal to 0. We can now solve that for V naught. V naught is going to be R sub 3 I sub 3 minus R sub 4 I sub 4. And remember what I sub 4 was. We just solved for that. We have R sub 3 I sub 3. I sub 4 was minus the sum of I1 and I3. We get rid of that minus sign, or two minuses make a plus, and we have r sub 4 times I1 plus I3. We can combine our I3 terms. And we have our I1. And remember what I3 was. We now have V naught is equal to R3 plus R sub 4 times I sub 3. But I sub 3 was just R1 plus R2 over R sub 3 times I1 plus R sub 4 times I1. Now we have everything in terms of I1. Let's just put all of that together. I'll write the first one first. We now have R4 plus, we have R3 plus R4 times R1 plus R2 all over R sub 3, all times I1. But remember, I1 was just Vn over R sub 1. Or, if we divide both sides through by Vn, we end up with A sub V, which is V naught over Vn, equaling R4 over R1 plus R3 plus R4 times R1 plus R2 all over R3 times R1, and that's now our gain that we want. Now that may not look like what the formula in the book states, but we can probably find what the formula looks like. Remember what we assumed. R4 was actually R2, R3 was R1, and R4 again was R2. This is R1 again, and we now have then that our gain, A sub V, is going to be R2, and let's just put this particular piece over R1 squared so that we get an R1 squared in both terms. So I now have R1 over R1 squared plus, and now I have R1 plus R2 squared over R1 squared. If we now start putting all of the pieces together, they all go over the same common denominator, R1 squared. I have R1 R2 plus the square of R1 plus R2, which is R1 squared plus 2R1 R2 plus R sub 2 squared. If I divide out the R1 squared, or divide that into all of the terms, well, before I do that, let me combine things. I now have R1 squared plus 3 R1 R2 plus R sub 2 squared all over R sub 1 squared. That now leaves me with 1 plus 3 times R2 over R1 plus R2 over R1 quantity squared, and that should look like the answer that they obtained for Part A. Part B wants us to find that particular gain expression for particular values of R sub 1 and R sub 2. Specifically, R1 is 10K, R sub 2 is 100K ohms. If we plug that into A sub V, we end up with 1 plus 3, and 100K divided by 10K is really just a power, or a factor of 10. Or we now have 1 plus 30 plus 100, or our gain is now 131. For Part C, what they were looking for was to find the input impedance. If we go back to our circuit, which is a few scrolls away, but now if we go back to our circuit, what we are looking for is we're trying to find the input impedance based on this input voltage and this input current into our system. That particular let me go ahead and get rid of that, because you'll wonder where that came from later, maybe, if you're looking at just the printout. So let me erase the magenta highlight. But now, if I want the input impedance, all I really need is to take the ratio of Vn to I plus, and I plus is 0, so the input impedance is infinity. Let me write that down. We know that Vn is going to be this Rn times In. In our particular case, we now know that In is equal to Vn over In, but Vn is okay, but In is I plus. We are working with an ideal op-amp, and so the current going into the input terminals is 0, which says that our input impedance is going to infinity. We now want to look at, or find in part D, the output impedance of our circuit, which means if we look back into our circuit from the output terminals, back in through where we've labeled V0, what do we actually see as far as an impedance? Another way of looking at that is if we look at the V0 equation that we derived, that equation did not involve this load resistor, or it was independent of R sub L. Because it was independent of R sub L, we can conclude, or therefore that implies that our output impedance is 0. Another way to think of that, let's just give another explanation maybe that might be helpful. Another way to think about this output impedance is the following. Suppose that we approximate or write down, so suppose we model the behavior of this op-amp circuit. Suppose we model its output side, or suppose we model the output side of the op-amp circuit with an equivalent circuit. What does that mean? Well, that means that we're trying to approximate, or basically model, the behavior of the output terminals. Here's our V0, but what we're saying is that V0 is going to be related to some gain in our system, which we calculated to be A sub V, Vn, and now we want to know what is this output impedance R0. What we're doing is we're actually hanging a load resistor onto our circuit. This is now the equivalent circuit that we're trying to find its behavior or characteristics. We've already determined that. We're trying to find this output impedance. If we just looked at this particular circuit and analyzed it, hopefully you can see that V0 is just a voltage divider related to that particular voltage. V0 is R sub L over R0 plus R sub L times this dependent voltage source's value, A sub V, Vn. But what did we just derive? We found in this particular circuit, op-amp circuit that we just analyzed, that V0 was equal to A sub V, Vn. That's what we just derived. That means that this R sub L over R sub 0 plus R sub L must actually equal 1 in order for us to have this relationship established. So this was due to our equivalent circuit. We found this voltage divider relationship. We've derived this from our op-amp circuit. Now we're trying to equate the two, and the only way that they are going to be equivalent is if this ratio RL over R naught plus R sub L is equal to 1. Well, that's possible. Or this relationship is possible if the numerator is equal to the denominator, or if R sub L is equal to R sub 0 plus R sub L. The way to force that to be true is if R sub 0 is 0, and that's our output impedance. So our output impedance, derived another way via an equivalent circuit, is equivalent to what, or consistent with what we had said before when we said V naught was independent of R sub L. Now we've derived the same output impedance value, which is 0, a different way.